Welcome to Team 2 Presentation 2 by Askar, Dorisonia, and Hargun. In this video, we will address aqueous equilibrium, question number 8 from the SmartWorks homework. Question number 8 states, a 25 milliliter sample of a 0.2100 molar solution of aqueous trimethylamine is titrated with a 0.2625 molar solution of HCl. Calculate the pH of the solution after 10, 20, and 30 milliliters of acid have been added. The pKb of CH33N is 4.19 at 25 degrees Celsius.
The first one is volumetric analysis. So for this definition, it's basically the measuring of a volume of a standard solution whose concentration is usually already known. So the most common way to figure this out is if you are in a lab and you put the unknown solution into a flask, and then you can use like a beret and just slowly spin it around, which is also considered titration. And this basically just measures the volume. Next, we have the definition of titration curve. So the titration curve is used to determine basically two things: the point at which the amounts of the acid and base are sufficient enough to cause basically complete neutralization, and its other job is to determine the pH of the solution at the equivalence point, which leads us into our next term, which is equivalence point. So at the equivalence point, you can see the change when all of the analytes have been consumed by the reaction with the titrants. A change in the rate of the temperature increases or decreases will usually reveal the equivalence points, resulting in the change in a curve. So since we talked about the equivalence point, I wanted to head down to the pH. And that's because the pH of the solution at an equivalence point is dependent on the strength of the acid and the strength of a base basically used in the titration. So for example, for a strong acid, strong base titration, which would have a pH equal to 7, is an equivalence point. And then for a weak acid, strong base, the pH will be greater than 7 at the equivalence point. And then for a strong acid, weak base titration, the pH will be less than 7 at equivalence point. Next, we have the half equivalence point, which is when the concentration of an added base is equal to half of the original concentration of the acid. So with that being said, the half equivalence point can be used to figure out the acid dissociation and pKa of the acid used in the titration. So your pKa's basically help you gauge the strength of your acid. What they do is they basically predict what a molecule will do in a specific pH and where it will accept or donate a proton. So when talking about accepting and donating protons, you can think about conjugate acid base pairs, because basically all acids have a conjugate base, which are made when their protons has been donated, and then the bases are basically formed when the protons have been accepted. Conjugate acid base pairs are also known to work as effective buffers, which will lead us into our next term, buffer solution, which is an aqueous solution that is a mixture of a weak acid and its conjugate base. So for buffer solutions, it's usually used to prevent any change in the pH of a solution, regardless of the solute that's used. So buffer solutions are basically used as a means of keeping that pH at a constant level. So for example, you can think about the blood in the human body as a buffer solution, keeping our body's pH at a constant. So when thinking of buffer solutions and keeping the pH at a constant, you also want to think about the buffering ranges, because its job is to stabilize the pH as well. It's considered the measurement of a buffer in resisting changes in the pH solution. So basically, this is the amount of strong acid or base that has been added to the solution to try to change its pH solution. So even though you have the buffer solution and the buffering range, trying to keep the pH at a stabilized and constant level This then leads you to hydrolysis, where the reaction mainly occurs between an ion and water molecules and often changes the pH of a solution. So it does play a huge part. This process is the chemical breaking of a bond within a molecule using just water in itself. So all in all, even though all these words mean different things, they all do play a role in solving this equation.
To solve a problem, first of all, we need to find the volume required for neutralization. To do that, we need to utilize the equation where V1 times M1 equal V2 times M2 and plug in the data that was given to us. The volume is equal to 20 mLs. In part 1, when 10 milliliters of HCl is added, we can apply Henderson-Hasselbalch equation to get the result, where POH equal pKb plus logarithm of salt concentration over base concentration, because that's what we're receiving when a little bit of acid was added. The POH is equal to 4.19, and to find pH we simply subtract the value from 14 to receive the final answer of 9.81. For part 2, when 20 mLs is added, there's only salt formed. So pH in this case would equal 7 minus 0.5 pKb minus 0.5 logarithm of salt concentration. And the answer is 5.37, which is the pH that we receive. For part C, when 30 milliliters of excess acid was added, the pH is equal to negative logarithm of acid concentration, and it is equal to 1.32.
Next, let's go over some essential concepts. Using the answers calculated in the above problem, we have drawn a titration curve of this weak base, trimethylamine, with a strong acid, HCl, to further analyze what is going on. On the x-axis, the volume of HCl added to solution is shown, and on the y-axis, the pH is shown. So titration curves are characterized by what looks like 3 distinct regions. First is the initial slight decline in slope, which in this graph is characterized from the pH values of 10.81 to 8.81. This is known as the buffer region and represents the range of pH values in which the pH differs very slightly upon addition of titrated HCl. When calculating the pH values in this region before the equivalence point, the equation CH3 to CH3 H plus OH minus is used to determine the amount of excess hydroxide ions that contribute to the POH value. Then from the POH value, you can calculate the pH. The second region, a distinct region on this graph, surrounds the equivalence point at 20 milliliters. The equivalence point is when all the moles of the solution, all the moles of the base in the solution have been titrated with moles of acid. You might expect that the equivalence point would have a neutral pH. While this is true for strong acid and strong base reactions, the reaction in this problem is for a weak base with a strong acid. Therefore, at the equivalence point, the pH is slightly more acidic rather than neutral at 5.37. The half equivalence point is interesting because it is the point at which the concentration of the added base is equal to half of the original concentration of the acid, or in this situation, the opposite. So the concentration of added acid is equal to half of the original concentration of the base. The half equivalence point for this problem is at 10 milliliters of HCl. This point is particularly important for calculations because according to the Henderson-Hasselbalch equation, the pH is equal to the pKa at this point. And the pH is 9.81. The last distinct region on this graph is after the equivalence point. At this point, you need to use the opposite equation that we were using before, quote unquote. You have to flip it so that you have CH3, 3NH plus dissociating into trimethylamine and hydronium ions. After the equivalence point, the hydronium ions are primarily responsible for the pH level.
Conclusion. In this problem, the solution of aqueous trimethylamine was titrated with various volumes of HCl. pH of the solution was found after 10, 20, and 30 mL of acid was added. Dilution was found via the equation M1V1 equal M2V2. Henderson-Hasselbalch equation was utilized to determine the pH. Equivalent point was determined to be 20 mL.